Sometimes you watch a chemical reaction and it just looks like like it's done. It stops fizzing, maybe the color stops changing. Everything just seems static.
Yeah, but what if that stopping point isn't really, things grinding to a halt at all?
What if it's something more active, like a perfect balance?
That's exactly the idea we're jumping into today. We're doing a deep dive into chemical equilibrium. It's this really core concept in chemistry that explains that seemingly static state.
Which is actually anything but static, right?
Absolutely. We've been looking through some chemistry resources, study guides and things to really get a handle on how reactions hit this balance point and maybe more importantly, what makes them shift.
So our goal today is to unpack what chemical equilibrium actually is, look at the factors that can nudge it one way or the other.
And even how we can predict, maybe even calculate where that balance point ends up. This is all for you to help you really grasp these key principles.
Okay, let's dive in then. The first big idea, I think, is that lots of chemical reactions aren't just a one-way street. They can actually go forwards and backwards.
Right. We call those reversible reactions. If you've seen them written down, you'll recognize that double arrow symbol. One arrow pointing right, one pointing left.
Yeah, that little guy.
That's the signal. It tells you reactants are bumping into each other, making products. That's your forward reaction. But at the very same time, the products are potentially breaking down or reacting to reform the original reactants. That's the reverse reaction.
And there's a really great visual example for this. The nitrogen tetroxide, which is colorless, reacting to form nitrogen dioxide, CnO2, which is this reddish-brown gas. So the equation is like AaN2O4.
That's a classic. It shows it so clearly. If you start with just the colorless in a sealed tube, you'll see it start to turn brownish as the CnO2.
And if you start with a red-brown...
Yeah. It'll get lighter as some of it turns back into the colorless. And here's the really cool part. Leave them long enough in that closed container, and they'll end up the exact same shade of reddish-brown. Doesn't matter which gas you started with.
So they reach the same endpoint. Which brings us right to the main idea. Dynamic equilibrium.
Dynamic, yeah. That's the key word. It's not static. It's not like everything has stopped. It's very much active.
Both reactions are still happening. Forward and reverse.
Absolutely. Both are still chugging along. Think of it like maybe a super busy doorway between two rooms. People are constantly walking back and forth. Reactants are still turning into products, and products are still turning back into reactants.
So what makes it equilibrium then?
It's when the speed of the forward reaction becomes exactly equal to the rate of the reverse reaction.
The speeds match. So the amount forming per second equals the amount reforming per second.
Exactly. The rate of product formation equals the rate of reactant formation. And because those rates are perfectly balanced,
the total amounts stop changing.
Precisely. The overall concentrations, the amounts of reactants and products you have in the container, they become constant. They don't change anymore.
Okay, that's a crucial distinction. It's the rates that are equal, not necessarily the amounts of stuff on each side. The amounts just stay steady.
Yes, super important point. Don't say the concentrations are equal unless they just happen to be in a specific case. They just remain constant because the opposing rates are equal.
Got it. Like a balanced tug of war. The rope isn't moving, but both sides are still pulling hard.
Good analogy. But for this whole balancing act to even happen, you need the right conditions. The system setup matters.
Right. You mentioned the sealed tube for the CeTO thing. That sounds important.
It is. You need what's called a closed system. If the container was open, what would happen?
Oh, the gases could just float away, escape.
Exactly. Like trying to boil water in a pot with no lid. Heat goes in, steam escapes out into the room. That's an open system. It exchanges matter and energy with its surroundings.
And the escaping steam means the reverse reaction condensation back into the pot can't really keep up, right?
Precisely. You can't reach equilibrium if one of your components keeps leaving. A closed system, on the other hand, is sealed off. Matter can't get in or out. Energy might still be exchanged, but the stuff is trapped inside.
And that trapping is key for equilibrium.
Essential. It ensures the reactants and products are always present, always able to react in both the forward and reverse directions until those rates finally do balance out.
Okay, so closed system, reversible reaction, dynamic equilibrium achieved when rates are equal, concentrations become constant. Got it. But what happens if you mess with it? Poke the bear, so to speak.
Now we get into the fun part, predicting what happens. There's a really powerful principle for this, called the Chatelier's principle.
Le Chatelier. I remember that name.
Yeah.
It's like the system's way of dealing with stress.
You could put it that way, yeah. The principle states that if you have a system at equilibrium in a closed system and you disturb it somehow,
Like change something.
yeah, you impose a change. The system will then shift its equilibrium position in a way that tries to counteract or oppose the disturbance you just made. It tries to reestablish a balance.
It fights back a little, tries to undo what you did.
Pretty much. It's resilient. And there are three main ways you can disturb an equilibrium. There's a handy mnemonic from the study materials, CPT.
CPT. Concentration, pressure, and temperature.
That's them. Those are the big three factors that influence the position of the equilibrium.
Okay, let's take them one by one. Concentration. What if you just dump in more reactant?
Okay, so you've increased the concentration of a reactant. Le Chatelier says the system will oppose this. How does it oppose having too much reactant?
By using it up.
Exactly. It favors the reaction that consumes that reactant. Which reaction is that?
The forward reaction. Reactants make products.
Right. So adding more reactant shifts the equilibrium to the right, favoring the forward reaction to make more product and use up some of that extra reactant you added.
And if you added extra product instead.
Same logic. The system wants to use up the extra product, so it favors the reverse reaction, shifting the equilibrium to the left, making more reactants.
What about taking something out? Like if you could continuously remove the product as it forms.
If you remove something, the system tries to replace it. So removing product pulls the equilibrium to the right. The forward reaction speeds up to make more product to compensate for what's being lost.
And removing reactant would pull it left, favoring the reverse reaction. Okay, it's always opposing the change, add more, use it up, take away, make more.
You got it. That's concentration.
Next up, temperature. This one felt a bit trickier. Depends on the reaction itself.
It does. It depends on whether the overall reaction releases heat or absorbs heat. Remember, exothermic reactions release heat, X is negative, and endothermic reactions absorb heat. Heck, it's positive.
Right, so heat is like a product in exothermic and a reactant in endothermic.
That's a really useful way to think about it for Le Chatelier. So if you increase the temperature, you're essentially adding heat to the system. How does the system oppose adding heat?
By using it up.
Yeah.
Absorbing it.
Yes. So it will favor the reaction direction that absorbs heat.
Which is the endothermic direction.
Correct. Increasing temperature favors the endothermic reaction. And if you decrease the temperature, you're removing heat.
So the system tries to produce heat. It favors the exothermic reaction.
Perfect. And this actually changes the equilibrium constant, Casey, which we'll get to. But for Le Chatelier, just think. Increased T favors endo, decreased T favors exo.
I remember seeing some data
Mm-hmm.
that CO2 plus solid carbon reaction making,
Really?
the numbers showed that at higher temperatures, you got a much higher percentage of CO.
Exactly. So what does that tell you about the forward reaction to the Fortio?
Well, if higher temperature favors making more, then that forward reaction must be the one that absorbs heat. It must be endothermic.
Bingo. The data confirms the prediction. Higher T favored the forward product side. Therefore, the forward reaction is endothermic.
Cool. Okay, last one of CPT. Pressure. You said this one's mainly for gases.
Right. Changes in pressure, which are usually caused by changing the container volume, really only significantly affect equilibria involving gases. And crucially, only if the total number of gas moles is different on the reactant side compared to the product side.
So you have to look at the balanced equation and count the moles of gas on the left versus the moles of gas on the right.
Precisely. Solids, liquids, even aqueous solutions aren't really compressed by pressure changes, so we ignore them for this effect. Just count the gas coefficients.
Okay, so what happens if you increase the pressure? Like you squeeze the butaner, decrease the volume.
You've increased the pressure. The system wants to oppose that increase. How can it reduce its own pressure?
By having fewer particles bouncing around, taking up less space.
Exactly. So the equilibrium will shift towards the side of the reaction that has fewer moles of gas particles. That side inherently occupies less volume, thus reducing the pressure.
Fewer gas moles helps relieve the pressure squeeze.
That's the idea.
Okay, let's take an example. The Haber process for ammonia, plus 3H2G, 2NH3G. On the left, we have 1 mole of N2 gas plus 3 moles of H2 gas. That's 4 moles of gas total.
Yep.
On the right, we have 2 moles of NH3 gas.
Right. 4 moles on the left, 2 moles on the right.
So if you increase the pressure on that system,
It will shift to the side with fewer gas moles to counteract that pressure increase.
which is the right side, the product side, with only 2 moles.
Mm.
So high pressure favors making more ammonia.
Exactly why they run the Haber process at very high pressures. Conversely, decreasing the pressure would favor the side with more gas moles, the left side in this case.
What if the moles of gas are the same on both sides? Like a CH2G plus I2G, that's 2 moles of gas on the left and 2 moles on the right.
Good example. In that case, changing a pressure has no effect on the position of the equilibrium. Shifting left or right doesn't change the total number of gas particles, so it can't use that mechanism to relieve pressure changes.
So pressure changes might speed things up, maybe, but they won't change the final ratio of HI to H2 and I2 at equilibrium.
Correct. No shift in the equilibrium position.
Okay, CPT, concentration, pressure, temperature, they shift the balance. What about adding a catalyst? Does that fit in here?
Catalysts are important, but they're special. A catalyst does not change the position of the equilibrium.
It doesn't, but catalysts speed up reactions.
They do, but here's the trick. They speed up the forward reaction and the reverse reaction by exactly the same factor.
Oh, okay, so both sides get faster equal.
Exactly. So the system reaches that equilibrium point where the rates become equal much, much faster. But the actual balance point, the final concentrations of reactants and products at equilibrium, remains unchanged.
So faster journey, same destination.
Perfect summary. No effect on equilibrium position, just on the rate of reaching it.
All right, so Le Chatelier helps us predict the direction of the shift, but you mentioned earlier we can put a number on where the equilibrium actually lies.
Yes. That's where the equilibrium constant, Kc, comes into play. The C usually stands for concentration.
Kc. So this is a quantitative measure.
It is. It's a value calculated from the concentrations of products and reactants when the system is at equilibrium. It gives us a fixed number at a given temperature that tells us the extent to which reactants are converted into products.
And how do you calculate it? I think I remember seeing an expression. Products over reactants?
That's the core idea. For a general reaction like Ca plus Bb, Cc plus D, the equilibrium constant expression is phase CCP/D.
Okay, so concentration of products in the numerator, concentration of reactants in the denominator. And the square brackets mean molar concentration.
Molar concentration, moles per liter, yes. And those coefficients from the balanced equation, the little A, B, C, D, they become the exponents for each concentration term.
Right, powers. And there's a rule about what not to include, wasn't there? Solids and liquids.
Very important. You do not include the concentrations of pure solids or pure liquids, L, in the Kc expression.
Oh, yeah.
Because their concentrations, their density or amount per unit volume, essentially remain constant throughout the reaction. They don't change significantly, so their constant values are kind of implicitly bundled into the Kc value itself. You only include species whose concentrations can change. Gases and things dissolved in solutions, Gaishelyi.
Okay, only gases and aqueous solutions go into the Kc expression. Got it. Now, we talked about CPT concentration, pressure, temperature shifting, the equilibrium position. Do all of those change the value of Kc?
This is a critical point. Of those three factors, temperature is the only mildly one that changes the actual numerical value of Kc.
Only temperature. Wait, so changing concentration or pressure shifts the amounts around, but the ratio defined by Kc stays the same for that temperature.
Precisely. If you change concentration or pressure, the system is temporarily knocked out of equilibrium. It then shifts, according to Le Chatelier, until the concentrations adjust back to the same ratio that satisfies the original Kc value for that specific temperature.
Wow. But changing the temperature.
Changing the temperature fundamentally alters the underlying energetics and kinetics. It changes the relative favorability of the forward versus reverse reactions in a way that establishes a genuinely new equilibrium position with a different ratio of products to reactants. Therefore, you get a different Kc value at the new temperature.
That seems really fundamental. Temperature and the inherent balance point are deeply linked.
They absolutely are. It connects back to whether the reaction is endothermic or exothermic and how adding or removing heat energy affects that balance.
So the value of Kc itself must tell us quite a lot then.
Definitely. The magnitude of Kc is very informative.
Okay.
If Kc is significantly greater than 1, say 100 or 10,000, it means the numerator products is much larger than the denominator reactants at equilibrium.
So mostly products. The reaction goes far to the right.
Exactly. Equilibrium lies far to the product side. The reaction strongly favors product formation.
And if Kc is much less than 1, like 0.01 or 1 times 10 to 5.
Then the denominator, reactants, is much larger than the numerator products. The equilibrium lies far to the left, favoring the reactants. Not much product is formed by the time equilibrium is reached.
And if PZ is like around 1?
That suggests that at equilibrium, there are appreciable concentrations of both reactants and products present. Neither side is overwhelmingly favored.
So a really tiny Kc, like 1.0 times 10 to 4 that was mentioned in the source, that means basically nothing happens. Mostly reactants left.
Pretty much. The forward reaction doesn't proceed very far at all under those conditions. Conversely, a huge Kc, like 1.0 times 104, means the reaction essentially goes to completion. Almost all reactants become products.
Okay. And we can actually calculate this Kc value if we can figure out the concentrations of everything at equilibrium.
That's right. Often you'll start with initial amounts, maybe in moles or initial concentrations. You might know how much of one thing reacted or what the concentration of one species is at equilibrium.
And you use the balanced equation stoichiometry, the mole ratios.
Exactly. To figure out how much everything else changed, there's a common method using what's often called an ICE table initial change equilibrium to organize these calculations.
Right, track the amounts. You might need to convert mass to moles using molar mass, or moles and volume to concentration.
All those standard chemistry calculations might come into play. Then, once you have all the equilibrium concentrations for the gases and aqueous species,
plug them into the Kekwe expression you wrote earlier.
Substitute the values. Usually use round brackets for substituting numbers, not square, which denote concentration of, and calculate the final Kekwe value. Remember, Kekwe itself doesn't have units.
Okay, so we can describe equilibrium, predict shifts with Le Chatelier, quantify it with Kekwe. Can we? Can we visualize it? See it happening over time?
Graphs are excellent for this. There are two main types you'll see.
Okay.
First, you can plot concentration or amount versus time. What would you expect to see there?
Well, reactants start high and decrease. Products start low, maybe 0, and increase.
And then what happens when equilibrium is reached?
The lines flatten out, become horizontal, because the concentrations aren't changing anymore.
Perfect. That flat line region on a concentration time graph is the equilibrium state. Constant concentration.
What's the other type of graph?
Rate versus time. This one shows the speeds of the reactions.
Okay. So the forward rate starts fast.
Yeah.
And then slows down as reactants get used up.
Exactly. And the reverse rate
starts at 0 if you only have reactants, then it speeds up as products are formed.
Right. And where do those two rate lines end up on the graph when equilibrium is reached?
They should meet it, become equal. Because that's the definition. Rate forward equals rate reverse.
Precisely. Equilibrium on a rate-time graph is where the forward rate curve and the reverse rate curve merge into a single horizontal line, indicating equal and constant rates. That really shows the dynamic nature.
And can these graphs show Le Chatelier's principle too? Like if you suddenly added more reactant?
Absolutely. On a concentration graph, you'd see the reactant concentration suddenly jump up vertically at the moment you add it. Then you'd see the reactant concentration decrease again, but maybe not back to the original level, and the product concentration increase as the system shifts right to reach a new equilibrium state with new constant concentrations.
And on a rate graph, if you added reactant,
the forward rate would instantly jump up because there's more reactant to react. The reverse rate wouldn't change instantly. Then, as the shift occurs, the forward rate would decrease from its peak, and the reverse rate would increase until they meet at a new equal rate.
What about adding a catalyst on a rate graph?
That's a neat one. At the moment you add the catalyst, both the forward rate and the reverse rate lines would suddenly jump up vertically because both are sped up.
Right.
They would then quickly become equal at that new higher rate. It shows you reach equilibrium faster, but the rates are still equal.
Wow. Okay. The graphs really do tell the story visually. It ties everything together.
It does, and it's not just, textbook theory or small lab experiments.
Right. This equilibrium stuff must be important in the real world.
Hugely important, especially in industrial chemistry. Think about making essential chemicals like ammonia via the Haber process or sulfuric acid via the contact process. These are massive equilibrium reactions.
And companies want to make as much product as possible, as efficiently as possible.
Exactly. So chemists and engineers use Le Chatelier's principle constantly. They carefully control the temperature and pressure conditions in those giant reactors to deliberately shift the equilibrium position as far as possible towards the product side, maximizing their yield. Understanding equilibrium is key to making those processes work economically.
So a lot packed in there. We started with this idea of reactions seeming to stop, but realizing it's actually dynamic equilibrium forward and reverse reactions happening at equal rates in a closed system, leading to constant concentration.
Then we saw how the Chatelier's principle lets us predict how that balance shifts if we change concentration, pressure, or temperature, the CPT factors. The system always opposes the change.
And that a catalyst speeds things up equally, but doesn't shift the final balance point.
Right. And we quantified that balance with the equilibrium constant. Khedive products over reactants raised to their coefficients, only including gases and aqueous stuff.
Crucially, remembering that only temperature changes Khedive's value.
Yes, and that the value of Khedive tells us whether products or reactants are favored at equilibrium.
We touched on how to calculate it, often using ICE tables, and how graphs of concentration or rate versus time give us a visual picture of the whole process, including shifts.
It's a really interconnected set of ideas that allows us to understand, predict, and even control how chemical reactions behave, from tiny test tubes right up to enormous industrial plants.
Absolutely. It really changes how you think about reactions. Which leaves us with a final thought, perhaps. If only temperature changes the equilibrium constant, Khedive, that number defining the natural ratio of products to reactants.
Yeah.
What does that really tell us about the deep connection between energy, which temperature relates to, and where a reaction fundamentally wants to end up? Why are some reactions just naturally product favored at room temp, while others barely go anywhere, all because of that temperature-dependent constant?
That's a great question. It probes the link between thermodynamics and equilibrium, something definitely worth pondering after our deep dive today.